Okay, so the first part that we have to review in logs is like, the major properties of the logs. So like, if you guys remember, if you got a to the power x is b, then we can write down this as x as log of b to the base a. Similarly, if you got e to the power x as suppose as b, then I can write down as x equals to ln b. Now, a lot of times the problem happen when students don't know how to convert from this to this. So I would recommend remember the shortcut. So suppose if you got log a to the base b equals to c, then we have this base out here. So a will be straight away b to the power c. So remember this is like, just one major hurdle that students don't know how to convert from the exponent to logs and logs to exponent. Now, as far as the properties are concerned, we have got, let's say, first properties, let's say log 1 to the any base a is 0. Then you have got log of a to the base a is 1. We have got log a to the power m to certain base. Now, if you have been given an exponent, like for example, log of 3 to the power 5 to the base 2 can be also written as 5 log 3 to the base 2. So this is logically speaking m log a to the base b. So this is the part where it is like, if you've been given any numerical value, and generally like in questions like these, for example, I have to evaluate 1 upon 81 to the base 3. Now, in such cases, you can just do log of 1 upon 81 can be written as 3 to the power of negative 4 to the base 3, because 1 upon 81 is 3 to the power 4. I mean, 1 upon 3 to the power 4. And if you take up, the indices become negative. So this basically becomes negative 4 log 3 to the base 3. And hence the answer is negative 4, because you know that log a to the base a is always 1. These are some of the basic properties. In the advanced properties we have got, suppose if you have got a product of two functions, let's say xy to the base a, this can be written as log x to the base a plus log y to the base a. Log x to the base a plus log y to the base a. Now, what does it mean is, suppose if you have got log of, let's say, x cubed y to the power 5 over, let's say division I'm going to do in the next property. So this can be splitted as log x cubed plus log y to the power 5. And this can be written as 3 log x plus 5 log y. So whenever there is no base, by default, we consider that base to be 10, as we know that. So if there is no base, like for example, if it's log x, sometimes it is also written as lgx. So they both mean the same thing, that this is to the base log of x to the base 10. If it is written as natural log ln x, so you by default here the base is e. So this is equivalent to log x to the base e. And e is nothing but a number, which is like, 2.771 and so on. It's like a irrational number, which is basically called also as Euler's number. So remember that these shortcuts are very important, and we have got 2-3 more properties that I would like to add and iterate. So the first thing is that if you got log x upon y to the base a, I can write down this as log x to the base a minus log y to the base a. So this is your division property. And one of the property that is like, I would say is the by far the most important property is also referred as change of base rule. So if you have got, let's say, certain base to a given number, suppose if you've got log a to the base b, I can write down this as log a to the base c over log of b to the base c. So you can attach any base that you want as long as it's positive number and not equals to 1. So if you have got, like, for example, log 3 to the base 5, a lot of times you'll notice that this can be written as log 3 over log 5. What does it mean is, here I have changed the base to 10. Now, by default, my base has become 10 here. So likewise, you can change this base to any other number you want. So let's say, for example, if you got log 3 to the base 5, I can write down this as log 3 to the base 2 over log 5 to the base 2. So you can attach any base as long as both the bases you're attaching is the same. Now, one of the very interesting outcome from here is, if you see, let's say log a to the base b can be written as 1 over log b to the base a. So from how do we get this result? So if you have got, let's say, log 3 to the base 5, I can write down this as 1 over log 5 to the base 3. So this is the general outcome or general understanding that we have to have for the log terms. Now, if you look at, let's say, log of 3 to the base 4, and suppose I wanted to change the base to 2. So this can be changed to base 2 by log 3 to the base 2 over log 4 to the base 2. So log 3 to the base 2 over log 4 to the base 2. Log 4 to the base 2 can be written as further log 2 square to the base 2. So this is log 3 to the base 2 over 2 log 2 to the base 2. And log 2 to the base 2 is nothing but 1. So that's where the answer is log 3 to the base 2 over 2. This is your basic understanding that is expected for log properties. So this is basically the properties of the logs part. Now we need to understand one of the interesting type of question that is assessed is the link between an exponent and log. So what is basically the link between exponential function and logarithmic function? So if you simply look at a function, let's say y equals to a to the power x function, which is referred as exponential function. So if I draw the graph of an exponential function, you will notice that the graph of this is an exponential nature graph, which is having the, like, the domain as x, or x belonging to real numbers. You can see that x can take any values, and range is basically y greater than 0, strictly greater than 0. Now, since we know that, if we find out the inverse of this function, let us see if we find out the inverse. So for inverse, we know that you interchange x with y and make y the subject of the formula. So if you interchange x with y, so a to the power y equals to x we get, and you get y equals to log of x to the base a. So y is nothing but log of x to the base a, which is like converting an exponent to log form. Now, if you notice this, log function has to be, so it means that log is the inverse of an exponential function a to the power x. So if you invert a to the power x function, you get log x to the base a. And since you know inverse functions are reflection in y equals to x line, if you draw the inverse reflection of this graph, so that will be here. And this is this any exponential function, standard exponential function cuts y-axis at 0, 1. This will be cutting at 1, 0. So this is about the exponential function, like, relation between them. So just let us take an example. For example, if you got y equals to 3 to the power x and y equals to log x to the base 3, it is asked what's the relation between these and how can you graphically link these two functions. So if you find the inverse of this function, you get this function. And if you find inverse of this function, you get e3 to the power x. So logs and exponent functions, they are mutually related through the inverse property. An inverse function you sketch by reflecting in y equals to x line. So that is about the reflection property. Now, what is really important is that every time you'll not just get these questions like log x to the base 3 or 3 to the power x. So a little more in depth, let us try to understand what if the questions are like, given on the logic of transformation. So now let us say, if you have been asked to kind of sketch certain graphs, like for example, y equals to, let's say, 3 times 2 to the power x, or y equals to 3 times 2 to the power x plus 5. or y equals to, let's say 3 to the power 2 raised to minus x minus 5. And then in general, if you have got y equals to a b to the power x plus c, how can we link up all these questions in a transformed approach or in a transformation approach? So basically, if you have got, let's say, a function 2 raised to x graph is something like here, and if you multiply, keeping the x values same, if you multiply y values by 3, you're going to get a graph basically more steeper, which is here. It's like this. So this is it's cutting here at 0 comma 1. This will cut at 0 comma 3. So this is referred as a vertical stretch factor by 3. So if you have y equals to 2 raised to x, y equals to 3 times 2 to the power x is referred as a vertical stretch factor by 3. So your domain and range still remain the same, but your graph has become now more steeper, and still this side will be asymptotic. This side will be asymptotic to the curve. So that's where the horizontal asymptote for 2 raised to x is still y equals to 0 function. Okay, there is no vertical asymptote for this function. Now, if you look at the contextual part of this transformation, it is a times f of x. This is a vertical stretch factor by a. So vertical stretch factor by a, when you do, you get this particular function. So now here also you should remember by heart that 3 times 2 to the power x is vertical stretch factor by 3. You take the original function as 2 raised to x and vertical stretch factor by 3, and then move the graph 5 units up. So if I look at this graph, so it is here. Now you'll have a new asymptote, which is y equals to 5, and your graph is basically going to become something like this. So this is going to cut here at 0 comma 8 now, because earlier it was cutting at 0 comma 3, and if you further move by 8 units up, you're going to get that. Now this particular question, now 3 times 2 to the power negative x minus 5, when you take 2 to the power negative x is basically reflection of 2 raised to x graph across y-axis. So 2 raised to x graph is like this. 2 raised to minus x graph will be something like here. So that's your exponential graph 2 raised to negative x. This is y equals to 2 to the power x. So whenever it is f of x and f of minus x graph, they are linked with basically reflection across y-axis. So here it is f of x graph is this, f of minus x is going to be this graph. And then vertical stretch factor by 3 and move 5 units down. So vertical stretch factor by 3, when you do, it is going to be something like this once again. And it will be 5 units down when you do, it is going to be something like here. This cuts at 0 comma 3. Now this will cut here at negative 2, because if you move the graph 5 units down, this will be cutting here at 0 comma negative 2. And still your asymptote is going to be y equals to negative 5. So in general, as a summary, if you remember, this c, y equals to c, is nothing but the horizontal asymptote to the graph. So any exponential function, if you're getting, this c represents the horizontal asymptote to particular given graph. So as a summary of this, you must understand how each transformation works. So just a quick jotting I'm giving here. If you got f of minus x, that's a reflection in y-axis, reflection in y. Negative f of x is reflection in x, reflection in x. So if you've got 2 raised to x graph and negative 2 raised to x graph, they are not reflection in y, they are reflection in x-axis. So negative 2 raised to x will be, first you reflect the graph in x-axis. Of course, you might be also knowing f of x minus a means a units to the right. F of x plus a means a units. This is to the right and this is to the left. F of x plus a means move the graph a units up. F of x minus a means move the graph a units down. So these are the basic transformations. And then you have AF of x, which is referred as a vertical stretch factor. So vertical stretch factor by A. Or you can also refer as vertical dilation by A. Dilation also means the stretch. So this is the graphical presentation of exponential form. I am hoping that it is clear now. So now when you look at the contextual part of the log graphs, as we know that y equals to 3 to the power x and y equals to log x to the base 3, they are basically the mutual inverses. So if you have got a graph like this, which is something here, this will be cutting at 1, 0. So if for any log graph, it might be little steeper or more steeper. But the x-axis, like if you have got log x to the base a graph, it is always going to cut x-axis at 1, 0. And here the interesting part that you notice is that there is a vertical asymptote compared to the exponential graph where you had a horizontal asymptote. So your graph that you have is going to have x greater than 0 as the domain and a greater than 0 also, because this is something very important, that x and a both are positive numbers. Also, a should not be 1, as a base should never be 1, because log of 1 to the base a, if I show it to you, like for example, if you have take base as 1, this becomes, by change of base rule, I can write down this as log x over log 1. And you know that log 1 is 0. So this is going to become undefined. That's why whenever base is not 1, that is what is recommended for writing the log term. So like your both x and a must be positive, but remember that base should not be 1 as well. So this is about the log concepts. Like remember that this is where a lot of people make mistake and don't understand the general graph idea, the correlation between both the graphs. So let us try to take a question which links actually two of the concepts and see how we can sketch one from the other one. So I'm just going to take the same graph 3 times 2 to the power x, let's say minus 5. And I wanted to first find out what's the inverse of this graph. So if I'm sketching the inverse of this graph, it will be x equals to 3 times 2 to the power y minus 5. So firstly, I'm finding out the function. So x plus 5 upon 3 equals to 2 to the power y. So y equals to, you get log of x plus 5 upon 3 and to the base 2. Now, reasonably, if you want to sketch this graph, I would prefer to sketch this one before this. Of course, you can apply transformation on this as well and get the graph, but I would prefer to sketch this and reflect in y equals to x line. So see now here, we can see clearly that y equals to negative 5 is the horizontal asymptote. So y equals to negative 5 is the horizontal asymptote. Then if you plug in x as 0 here, you'll get the y-axis intercept is negative 2, because 3 times 2 to the power 0 is 3 minus 5 is negative 2. So this will cut here somewhere at negative 2. And then this is an asymptote. So your graph is basically something like here. So this is the graph of the exponential function. It will not go below y equals to negative 5. So this side, the graph is looking like this. Now, if you wish to sketch this graph, by default, you can just do one thing, is reflect this in y equals to x line. So for example, if you got, I'll just take the different color. So vertical asymptote now is going to become basically x equals to negative 5. So your graph will have a vertical asymptote as x equals to negative 5. So you can see the domain of this function was all real numbers and range was y above negative 5. So for x equals to negative 5 graph, your the log graph, your domain will become x greater than negative 5. So this side, it is going to be x greater than negative 5. So if you reflect in y equals to x line, this is how your graph approximately will look like, and it will never ever be like here. So this is how you do this graph. So in the first example, what we have is basically the question is solve for log x to the base y plus 2 times log y to the base 4 equals to 8. So find out the value of x and y. So when you're solving for this, it'll be basically, you can notice the first discrepancy is the base out here. You change the base to 2, that's the ideal one. So this you keep it as it is. This can be written as log y to the base 2 over log 4 to the base 2 equals to 8. So log x to the base 2 plus 2 log y to the base 2 over log 4 to the base 2 is nothing but 2. So this 2 and 2 get cancelled, equals to 8. So we get log x to the base 2 plus log y to the base 2 equals to 8. So this is going to become log xy to the base 2 by like using the product property in reverse way equals to 8. So xy is going to be 2 to the power 8, and that's what is the answer for the first part. So for the second part, we have to make the substitution of 2 to the power x they have given us to solve this particular equation. So if you got 2 to the power 2x plus 1 minus 2 to the power x plus 1 minus 2 to the power x plus 1 equals to 0. So it is always recommended that you break this up as 2 to the power 2x times 2 to the power 1 minus 2 to the power x times 2 to the power 1 minus 2 to the power x plus 1 equals to 0. So if I take, let's say y is 2 to the power x, y squared is going to be 2 to the power 2x. So you get this as 2y squared minus 2y minus y and plus 1 equals to 0. So here is the main problem. Like, you need to understand this. So if you have got 2 to the power x is y, if you square both the sides, you get y square value. So y square is nothing but 2 to the power 2x. So this 2 as it is, I kept out here, and 2 to the power 2x, I wrote it as y squared. So 2y squared minus 3y plus 1 equals to 0. And if you factorize this part, so 2y squared minus 3y plus 1, if you factorize it, you're going to get this as 2y squared minus 2y minus y plus 1 equals to 0. Product is 2 and sum is -3. So that's your -2 and -1. So if you take 2y common, you get y minus 1 minus 1 y minus 1 equals to 0. You get y minus 1 and 2y minus 1 equals to 0. So either y is 1 or y is half. So either you get 2 to the power x is 1, which gives us x as 0, or 2 to the power x as 1 by 2, which gives us 2 to the power x is 2 to the power -1, which gives us x as -1 as the answer. So this is the more of the exponential question. So the first question is basically you have been given log x to the base a is p and log y to the base a is q. You have to write down this in terms of p and q. So first you apply product rule. So it will become log a to the base a plus log x to the base a plus log y squared to the base a. And log x to the base a is nothing but p. And the second part, log y squared to the base a, can be written as 2 log y to the base a. So 1 plus p plus 2q. The second one, we have got log x cubed to the base a minus log 8y to the base a. You further apply product rule on this, so it becomes basically this part, log a to the base a plus log y to the base a. So 3, this is 3p minus 1 and minus q. Then this part we have got log a to the base x will be 1 upon log x to the base a, because you know that log a to the base b can be written as 1 upon log b to the base a. And from here you can go to here as well. So log a to the base x, I wrote it as 1 upon log x to the base a plus 1 upon log y to the base a. So this is 1 upon p plus 1 upon q, because this part is p in denominator, this part will be q in denominator. And so that's how I got that. The last part is if you have to write down, solve for 3 to the power x minus 3 times 3 to the power of 1 plus 2x plus 4. So take substitution as 3 to the power x. So it'll become 3 to the power x minus, you break this down as 3 to the power 1 into 3 to the power 2x. So this is what you get. And then 3 to the power 2x is m square. So it'll become m minus 3m square plus 4 is 0. So if you bring it everything to the right side, you get 3m square minus m minus 4 as 0. Factorize it and solve, you get m as 4 by 3 and m as -1. Now since 2 to the power x, 3 to the power x can't be -1, so this is gone. So 3 to the power x is 4 by 3. So x is basically log of 4 by 3 to the base 3. That's your basically the answer to this particular question. So here for this particular question, first you have to write down these indices in the form of p to the power a, q to the power b, and r to the power c, where p, q, r are the constants. So basically you're trying to break this down as a powers of p, q, and r. So here the best strategy is to simplify firstly each power. So root p can be written as p to the power half, then q square, p square upon r square, and divided by p to the power minus 1, q to the power 1/3, and r to the power 1/3. Cube root can be written as to the power 1/3. After this, the interesting thing is that you got to simplify all of these. So first you do p to the power half, q to the power 2, p to the power 2, r to the power negative 2. So this goes up and become r to the power negative 2. And if these go up, they become p to the power 1, q to the power negative 1/3, and r to the power negative 1/3. Now after this, you combine the powers. So combine the powers of p. So p is half plus 2 plus 1. So it's basically power of p is 3 plus half. 3 2s are 6, 6 plus 1, 7. So p to the power 7 over 2. Then you get q power. So power of q is 2 to the power q to the power 2 minus, there are only 2 q's that I can see. So q to the power 2 minus 1/3. So it will be q to the power 5 by 3. And then we have got r powers. So r to the power negative 2 into r to the power negative 1/3. So it become r to the power negative 7 by 3. So that's your like so the value of a is 7 by 2, value of b is 5 by 3, and value of c is minus 7 by 3. So this is the first part explanation. Next one is when you have log x to the base 2 plus 2 log 7 to the base x equals to
So it's x to the base 7, not 2.
yeah, so we have got, let's say, log x to the base 7 plus 2 log 7 to the base x equals to 3. So we have to solve for x. Now here what we do is basically let log x to the base 7 plus, now this log 7 to the base x can be written as 1 upon log x to the base 7. So this 2 as it is equals to 3. Now take log x to the base 7 as, let's say, t. So it'll become t plus 2 by t equals to 3. So take LCM of this, you'll get t square plus 2 equals to 3t. Now you'll get t square minus 3t plus 2 equals to 0. So I have taken basically t as log x to the base 7. That simplifies our calculation to a certain extent. Now you factorize this, you'll get t minus 1 and t minus 2 equals to 0. So you get t as 1 and t as 2 basically. So you get log x to the base 7 as 1 and log x to the base 7 as 2. So this results in x as 7 to the power 1, which is 7. And second one results as x as 7 squared, which is 49. So this is one of the important type of question. This has been assessed several times in the exam. So I strongly recommend you to kind of remember this method. So the first part is log x to the base 3. So if you have taken, let's say, u as log x to the base 3, obviously in this case you first change the base to 3, so it'll become log x to the base 3 plus log x to the base 3 upon log 9 to the base 3 equals to 12. So log x to the base 3, you take it as u, so it'll become u plus, and this is log 9 to the base 3, which is 2. So u plus u by 2 equals to 12. So these are, like, good strategies that if you substitute something, let's say take log x to the base 3 as u, and it simplifies the way you look at this problem. So it's always good and recommended that wherever you see like terms, you can substitute something and then you resubstitute back once you get the answer. So 2u plus u upon 2 is 12. So you get 3u equals to basically 24. So you get u as 8. So you get log x to the base 3 as 8. And as a result, you get x as 3 to the power 8. So this is the exact answer to this question. So this is log 3y square minus 10 to the base 4 equals to 2 log y minus 1 to the base 4 plus 1. So now here you notice that the bases are the same. The marks is 5 marks. It means that there has to be some tricks in this question. So first you bring in this thing here. So it'll become log 3y square minus 10 to the base 4 minus. And you can pull back power to 2 to the back to the power. So it'll become log y minus 1 the whole square to the base 4 equals to half. So you get 3y square minus 10. If you apply the division property over y minus 1 the whole square equals to half. So this will become 4 to the power half, which is 2. So 3y square minus 10 equals to upon y minus 1 the whole square equals to 4 to the power half. So this, which is 4 to the power half, is 2 root of 4. And then you solve for y. So you'll get a quadratic. You open it up. So 3y square minus 10 equals to 2. Y square minus 2y plus 1. Then you open the bracket. So 3y square minus 10 equals to 2y square minus 4y plus 2. Bring in everything one side. So you get y square. Bring it 4y to the other side. Y square plus 4y, and then minus 10 plus 2, so it will become minus 12, or if you move 2 to the other side. So you got equation y square plus 4y minus 12, and if you factor this out as 4 and 2, 6 and 2, negative 6 and positive 6 and negative 2, so you get y square plus 6y minus 2y minus 12. So you take it 0. So y plus 6 minus 2, y plus 6 equals to 0. You get as y is 2 or y is negative 6. This is the answer to this particular question. We should always verify. Now see, for example, y is negative 6. If I take this term, become undefined. So negative 6 minus 1 become log of negative 7, which is not possible. So you got to reject this and take the only value that is approving, which is like y equals to 2. So this is about this particular question. So linear law basically is, suppose there are certain graphs which are not like linear in nature. Now if you look at y equals to ab to the power x, this is an exponential graph. So what happens is that if we can make certain adjustment, we can convert this graph y equals to ab to the power x into a linear function. Now, for example, if you got a b to the power x, if I just take log both the side, now how do I know what do I need to take? So most of the time you'll notice that on the graphical axis, you have the right quantities that they're described that are giving a linear nature of the graph. So if I take natural log both the side, this is ln a b to the power x. So this will become ln y equals to ln a plus ln b to the power x by a property. So ln y equals to ln a plus this is going to become, if you take LCM here, this is going to become x ln b. I mean, LCM means apply the property. So that is going to become x ln b. Now, what do you do is basically take ln y as capital Y. So take ln y as capital Y, you can see here on y-axis. And so this is going to be ln b. So if you compare y equals to mx, so m capital, let's say x plus c. So here if you see c is your ln a and m is nothing but ln b. So slope that you have got, slope of the line is the m value. So which is here, which is 10 minus 4 upon 8 minus 2, which is nothing but 1. So ln b value, that's your slope. So ln b is your slope, which is 1. So that gives us b as e to the power 1. Secondly, to get the y-intercept is ln a. So first you find the equation of this line. So you take capital Y equals to m capital X plus c, always, irrespective of whatever is on y and x axis. So take these coordinates. So take y equals to m is 1. So it will be x plus c. Then you take x as 2 and y as 4. So 4 equals to 2 plus c. So c equals to 2. So your equation basically is y equals to x plus 2. That's your equation. Now they asked us to write down the value of a and b. So slow, since y-intercept is 2, my y-intercept according to this graph is ln a. So ln a is 2. So I get a as e to the power of 2. So answer for a and b, you can find out using this logic. Now in short, what you got to do is, whatever quantity they have given on x and y axis, you first find out a straight line equation for it. Like take capital Y equals to capital mx plus c. Then you substitute what are the actual values of y. Sometimes they'll not give you this result, sometimes they'll not tell you this thing, but they'll just give you equation here and they'll ask you write down y in terms of x. So here, since a and b already they have given that this is exponential form, you don't need to worry about. But suppose this was not given to us, then how would we do this problem? So what would be our approach? So in that case, I'm going to just write down the equation y equals to x plus 2 as we got that. Now you see what is substituted on y-axis. So on y-axis, ln y, and on x-axis, it's x. So ln y equals to x plus 2. Now you make y the subject of the formula. So y will be e to the power x plus 2. Now if you break this down, it will be e to the power 2 into e to the power x. And you can compare and see that this is pretty much similar to what we got. So e squared, we got it as a, and b we got also as e. So which was like, pretty similar to what we had done and what we had like, got in the previous question. So sometimes you need this skill like forward, backwards application of log concept in order to get the correct answer.